Hello everybody, this is the first class on sequential circuit analysis and design. As you know, we have covered a wide spectrum of different combinational circuits so far, and none of those circuits included any memory in it, and we would like to store bits in our digital circuits, right? So in today's class, we will introduce circuits with memory logic unit called sequential logic circuits. We are particularly interested in the design of memory elements and clock sequential circuit analysis. Such digital circuits lay the foundation of digital storage technology and are found in almost every modern digital device. And today's topic is much wider than the material that we will cover here. However, hopefully future classes will have short discussions on those future-related and more advanced circuits and systems. So a sequential circuit is specified by a time sequence of inputs, outputs, and internal states of the circuit, in contrast to a combinational circuit and whose outputs solely depend on the inputs. A combinational logic interconnected with storage elements give rise to what's called sequential circuits. The block diagram in the slide shows that the outputs in a sequential circuit are not only function of the inputs, but also of the present state of the storage elements, or memory elements. There are two types of sequential logic. One of them is called synchronous, the other is called asynchronous logic. In this class, we'll only dwell on the synchronous type, and we may have some discussions on asynchronous logic sometimes, but majorly we'll be focusing on synchronous type, in which the signals affect the storage elements at only discrete instants of time. Synchronization is achieved by a clock generator, which generates a periodic train of fixed clock pulses. Clock pulses determine when computational activity will occur within the circuit. Next, we will cover logic circuits with feedback that are the basis for storage elements and memory. A storage element can maintain a binary state indefinitely until changed by an input signal that is external to the circuit, and then it switches the state of the circuit. The most basic storage element is known as the SR-Latch, where S means, or it stands for set, and R stands for reset. SR-Latch can be manufactured using two NOR gates, as shown, and the truth table for this circuit is given to the right of the logic diagram. And if you follow the wires and think about binary signals flowing in and out of the circuit, you will see that state 00 is the state table is in the state table that SR-Latch uses to store bits. When the S input is set to 1, then the latch is called set, and in which case the Q output becomes 1 and Q prime becomes 0. When the S input switched back to 0, the outputs Q and Q prime stays the same, and hence the latch is set. A bit 1 is stored. Until one of the inputs is changed to 1 again, and if R is set to 1, on the other hand, instead of S, the latch is set to reset state. An alternative way of representing the truth table of all these circuit operation uses state functions. QT and QT plus 1. QT represents the current state, and QT plus 1 represents the next state. And as you can see from this simple state table, the SR00 state, the 00 state holds the state. So when you complement the S and R inputs of the NOR implementation of the SR-Latch, we get the truth table for the same latch implemented with NAND gates this time. That's why NAND gate implementation is sometimes called S prime R prime latch. Based on this observation, we can state that 1 is the stable state for this NAND implementation, and 00 now becomes the undefined or metastable state, and it's forbidden usually by the designer. The state table and the truth table, in fact, is shown to the right of the logic diagram in this slide. SR-Latch can be modified by adding a control input. The control signal acts like an enable signal. When the enable signal is 0, the input to the SR-Latch is 1, 1. This is the stable state for the SR-Latch. When enable signal goes 1, information from S or R input is allowed to affect the latch. When the circuit is enabled and the set state is reached when S equals 1 and R equals 0. To change it to reset state, first S should go to 0 and then R should go to 1. When the enable signal goes 0, the current state of the circuit is retained. All these possibilities are summarized in the table shown to the right of the logic diagram. When all the inputs are active 1, the latch goes into undefined state and the next state cannot be conclusively known. This state is seldom used. To eliminate this state, we can devise a latch configuration called D-latch as shown at the bottom of the slide. This way, the SR-Latch with control input can only have SR input set to 0, 1 or 1, 0 because the leftmost NAND gate in this logic diagram acts like an inverter, making the latch input 1, 1 impossible. The truth tables are also shown in terms of state functions. The D-latch is also known as transparent latch because when it's enabled, the input appears at the output unchanged. Upon the deactivation, the state of the latch is preserved. The output follows the input stream, of course, within 2-level gate delays until the enable signal is deasserted, in which case the binary information that was present at the data input at the time the transition has occurred is retained or stored. The previous 5 NAND implementation of D-latch can be improved by observing the following chain inequalities. Using De Morgan's law and also some of the theorems that we've covered in our previous lectures. Therefore, we can use only 4 NAND gates to implement the same functionality, D-latch. Latches show changes to positive value, but we usually need circuits that will show response to signal transitions. These circuits are called flip-flops. The state of the latch can be changed by a change in the control enable input. Therefore, a latch with pulses at the control or enable input is essentially a flip-flop, which is triggered every time enable and signal goes to logic 1 value. However, while the latch is active and inputs change due to some other combinational logic, the state of the latch will change, producing multiple outputs at the given clock or pulse width. This creates a serious challenge and unpredictable outcomes for synchronous logic circuits. Due to this unreliable operation, latches are usually not used to design memory elements. Flip-flops are storage elements controlled by a clock transition instead of signal levels. Therefore, the flip-flops are triggered during only a signal transition. Flip-flops are constructed such that they operate using a common clock of the system, and they respond to inputs only at clock transitions. In a latch, as long as the clock or the signal, control signal in our case, is positive, the circuit is responsive. That's usually a very long time for fast hardware. The key feature of flip-flops is the trigger effect, only at signal transitions. A clock signal can go through transitions from 0 to 1, named positive edge trigger, or 1 to 0, called negative edge trigger, as shown in this picture. There are 2 ways to design an edge-sensitive flip-flop. The next slide will discuss these approaches. So we will discuss D-flipflops first, which is quite popular and can be used to implement other flip-flops. D-flipflops can be constructed using 2 design approaches. One of those approaches involves 2 D-latches, one in master mode and in another in slave mode. And this configuration is shown in the slide on the top. First, the master latch is activated with a positive clock level. The input is sampled and transferred to the output Q. As the clock signal transitions to 0, the slave latch becomes activated and the master latch goes into hold state. And the D value stored in the master latch in the previous round is transferred to the output of the flip-flop. Therefore, the output can only change with the negative edge of the clock. The idea behind using 2 latches is that even if the input D changes while the slave latch is active, since the master latch is disabled, its effect will not be propagated to the flip-flop output. Therefore, the circuit behaves like a flip-flop. Alternatively, we add an extra inverter between the clock input and the junction between the enable input of the master latch and the other inverter. This is shown at the bottom of the slide. This makes the flip-flop positive edge triggered. Another approach is to use 3 SR latches in a special configuration as shown to the right of this slide. When clock is 0, the S and R inputs of the third latch is kept at 1. The stable state which holds the data. While D equals 0 and clock becomes 1, the reset input of the third latch will turn 0, making the output Q equal to 0. Note that even if D changes while the clock is high, the reset input R will still stay at 0, therefore making the whole circuit edge triggered. When the clock returns to 0, R goes to 1, and therefore the third latch goes back to stable state, and the output will be held at the present state. Similar steps can be followed to see when D equals 1 and clock becomes 1, the third latch will be set and the Q output will be equal to 1. Any further changes at D will not affect the circuit. All in all, this flip-flop is therefore a positive edge-triggered D flip-flop, where the D input is transferred to the output at positive clock signal transitions. The block diagram for D flip-flop is shown at the bottom of this slide for both positive and negative edge-triggered cases. Although the most economical and the efficient flip-flop is the edge-triggered D flip-flop because it requires the least number of gates, there are also other types of flip-flops that can be constructed using D flip-flops and some external logic. Two other less widely used flip-flops are called JK and T-flipflops. First off, I would like to remind you that a generic flip-flop serves 3 basic missions besides storing a single bit for a digital system. It can either set the output to 1 or reset it to 0 or complement the output. The JK flip-flop is the most general form of all, and it's capable of performing all 3 basic functionalities. J input sets the flip-flop to 1, K input resets it to 0, and when both inputs are active, the output is complemented. We can realize a JK flip-flop using a D flip-flop and few external gates as shown to the left of the slide. And we can verify the relationship between the D input of the flip-flop and the JK inputs. The T or toggle flip-flop is a complementing flip-flop and can be obtained from a JK flip-flop by connecting the J and K inputs to make them equal to each other. This gives us the implementation shown to the right of this table. When T equals 0, a clock edge does not change the output. When T turns 1, a clock edge will complement the output. If you think of us sending 1s to the input of the T flip-flop, the circuit is adding. In other words, XORing the 1s. So T flip-flops are useful for adder implementations or counter implementations. For sequential logic, we also need the state information to be present in the truth table. So if we add this information to the truth table, the new table is usually called characteristic table of the circuit. In this table, Q2 refers to the present state and QT plus 1 represents the next state. QT does not change to Q2 plus 1 unless a clock edge occurs and activates the circuit for a potential new state. The characteristic tables and equations are shown for all 3 flip-flops we have covered so far. Note that T and D flip-flops have 2 rows in their characteristic table, and therefore JK flip-flop can be obtained by merging these 2 tables, which makes JK flip-flop, in fact, is the most general form of the flip-flop topology we have seen. This discussion finishes our conversation about the memory elements constructed using latches and then flip-flops that are able to hold the states and therefore store bits for as long as needed. Next, we dive into the analysis of sequential circuits. The behavior of a clocked sequential circuit is derived from the inputs, outputs, and the present state of the flip-flop. The analysis of a sequential circuit is all about determining the time sequence of inputs, outputs, and the internal states. One of the important tools for the analysis is the state equations. A state equation specifies the next state as a function of the present state and the inputs. Second important tool is the state table. A state table is used to enumerate all of the possible present and next state conditions with the corresponding input and output values that are going in and coming out of the system. This table can be found using the state equations by walking through all possible input and state combinations. Final tool, which is nothing much different than the state table's representation, is called the state diagram. A state diagram is another way of representing the state transitions and input-output relationship of the state table. So the overall analysis procedure starts with the given sequential circuit that can have flip-flops and few combinational logics around it. We first find the state equations, which shall lead us to draw the state table. By modifying the state table, we finally obtain the state diagram of the sequential circuit. By looking at the input-output relationship and the state in the state diagram, we understand what the circuit is doing. Let us walk through an example to see how such tools become useful and help us understand how the overall analysis works. Here we present an analysis with D-flipflops using a circuit that has 2 D-flipflops in it and a bunch of other gates around it. The first step towards the solution is to write down the state equations. There are 2 state equations for this circuit, and they are AT plus 1 equals ATXT plus BTXT, and BT plus 1 A prime T and XT. There is also one output function, YT, and it's just given by AT plus BT in parentheses, and with X prime T. By the way, this example is borrowed from our reference book by Dr. Mano and his colleague. Next, from the state equations and output function, we derive the state table, consisting of all possible binary combinations of present states and inputs. We have 2 flip-flops and 1 output, which makes 2 to the 3 rows in our state table. In general, if we had n flip-flops and m output signals, then the state table would have 2 to the m plus n rows. As you can see, the state table has 2 A's and 2 B's. One of them represents the present state and the other represents the next state. As long as we know the relationship between the state and transitions based on the inputs to the circuit, we can characterize the behavior of the circuit. An alternative way of representing the state table is shown bottom left of the slide. In that table, the input column is divided into 0 and 1 input cases. And for each, the next state is written as a 2-tuple binary number. This alternative representation is pretty useful for producing the state diagram of the circuit, as we will draw it next. State diagram is drawn from the state table. Each combination of the flip-flop values represents a state. Hence, if there are m flip-flops, then we can have up to 2 to the m states. In this example, we have 2 flip-flops and therefore 4 states. Each state is denoted by a circle. Each arrow between 2 circles denotes a transition of the sequential circuit, a row in the state table. A label of the form A/B is attached to each arrow, where A denotes the inputs, if there is any input to the circuit, of course, and while B denotes the outputs of the circuit, output or outputs of the circuit in that transition, of course, if there is any output. As you can see from this example, let us assume we are in the state 0, 0. Then an input X equals 0 keeps us in the same state at each edge of the clock pulse and gives an output of Y equals 0. After the first one's appearance and all the ones afterwards at the input, the circuit travels across states 0, 1, 1, 1, and 1, 0, and stays there until a 0 is inserted into the system, in which case the output turns 1, indicating a 0 is found. You can also observe all states are going back to state 0, 0 whenever the input becomes 0. Therefore, this circuit can be used to detect zeros in the input bit stream. The analysis work for the following sequential circuit that uses 2 JK flip-flops, 2 XOR gates, and 1 inverter is left as an exercise, actually in-class exercise. Finally, I'd like to talk about 2 distinct sequential circuit models, namely Mealy and Moore machines. These 2 models of a sequential circuit are usually referred to as a finite state machine, abbreviated as FSM. They differ only in the way the output is generated. For instance, in the Mealy model, the output is a function of both the present state and the input. On the other hand, in the Moore model, the output is purely a function of the present state. These models can be represented using 3 circuits in cascade. front-end and back-end combinational circuits, and in between the state registers. Feedback is provided for correct memory realization in both circuits. In the Mealy model, the inputs are also used to compute the output, whereas in the Moore model, the output is the output of the back-end combinational circuit, which are direct consequence of the present states only. Our previous exercise is an example of the Mealy model. Think about whether the in-class exercise is a Mealy model or a Moore model. So therefore, in this class, we covered the fundamental building blocks of storage systems. In other words, the memory elements. These circuits have feedback associated with it, which enables them to have states in them. Next, we learned about how to use such elements to draw clocked or synchronous sequential circuits. Finally, we have learned how to analyze a given sequential circuit using state equations, tables, and diagrams. After learning about memory elements and analysis in this lecture, in the next lecture, we will learn about the synthesis of sequential logic circuits and their strict design rules that differ from our conventional combinational logic design rules. We will also touch upon the similarities and complement our background with new tools and information. Please feel free to drop any questions you may have about today's lecture into my email box, and I'll be more than happy to help you with your questions. Thanks a lot.